BKW Physics. I'm Mr. McConley, and today we're going to talk about the speed of light. How did someone find the speed of light? Now, if we back up in history, the early Greeks wanted to know how fast light traveled. But it was confusing to them because basically they're like, as soon as my eyes open, or as soon as I look at the light, it's there, like it's instant. They thought it was like basically instantaneous, like light was there immediately. And then other people started thinking about it later in history. Ole Romer was a Danish astronomer, and he was basically around 1700. And he looked at Jupiter's moons, and he was actually able to figure out a rough estimate of the speed of light because he noticed that as the moons rotated around Jupiter, when they were moving away from him, he got different measurements than when they were moving towards him. And he kind of figured out, oh, that must have something to do with the fact that light does have a speed, and so he started making some calculations. We're not going to go into that, because he didn't come up with the number. Galileo did experiments where he held lanterns on separate mountains, and he would like uncover a lantern, and then he would try to time it, but of course his timing devices weren't nearly adequate for the speed of the light. The guy that was successful is Albert Michelson. He lived from 1852 to 1931. He was an American physicist, and he is credited with finding the speed of light, a great accomplishment. Here's how he did it. He had a device, an octagon, and it was an octagon that could spin. He could control the speed of this. And the octagon had one mirrored surface. So it had 8 surfaces, and one of them had a mirror attached to it. So let's say the mirror was down here, okay? If the mirror is down on this surface, he had a light source. Now it wasn't a light bulb, but it helps you visually see what's going on. So the light source would hit the mirror, and because of the angle of incidence equaling the angle of refraction, the light would bounce off. It would travel all the way down here to the other end, and it would hit a concave mirror, a curved mirror. Angle of incidence equal the angle of refraction, it would bounce off. Then it would hit a convex mirror, bounce off, hit the concave mirror again, and be sent back. Basically, this part right here, this whole contraption here, is just so you can send the light in and then kind of move it over a little bit. Now, when the light comes back, it travels all the way back this way. Those lines are supposed to be perfectly straight and parallel. If this has rotated so that the mirror has gone from here to here, then the light will bounce off the mirror and come up, and this is Mr. Michelson here. If you can't tell my sad drawing. This is Mr. Michelson. He will see the light again, and if he sees the light, he knows that the mirror has rotated that much. He can figure out the speed of rotation, the RPMs, not RMPs, RPMs, rotations per minute. He can figure out, oh, I know the RPMs, therefore I know how much distance it moved. If you can figure out the distance, you can figure out how much time, and you can do distance divided by time, and that's velocity. So that's a good question. How far, distance-wise, did the light travel? Now some of you are looking at this, no, like the length of the whiteboard. Well, I just drew it that way so you could see. In actuality, this distance down and back was 35 kilometers. This was a huge experiment, a huge setup. If you think about 35 kilometers, and what he did is he used vacuum pipes. So you can kind of visualize or draw a pipe surrounding this light. So what's happening is the light is traveling through this pipe, and he evacuated. He made this a vacuum, so that he pulled all the air out, so that the air wasn't affecting anything. It was just traveling through a vacuum pipe. So the light would come down and back 35 kilometers, super long distance. Must have been so hard to get that straight and the vacuum and everything. A lot of work to get this to happen, but eventually he did get it to happen, the light went down and back. He controlled the speed until he got the speed right. He plugged in his distance. He plugged in how much time. And he calculated the velocity of light to be what he came up with. And he called the speed of light c. Okay? Called the speed of light c. And he calculated it to be 299,792,458 meters per second. What we use in physics, we call the speed of light, we still call it letter c. We use 3.000E8 meters per second. Now, one more little thing. We've been using the equation v equals f lambda a lot recently. This equation is still perfectly correct, and some people like to write the equation c equals f lambda when they're specifically talking about a problem involving light. You don't have to. If you understand that c and v are the same thing, you don't need to change it. But some people do write it that way. So that's how Albert Michelson calculated the speed of light. Physics.